of these different modalities, each with its own advantages and disadvantages. Except for ultrasound and MRI, all these diagnostics involve radiation. At the end of this lecture, it is expected of you to gain more knowledge on the structure of the atom, elementary nuclear physics, the nature of electromagnetic radiation, and the production of X-rays. So radiation may be classified as electromagnetic radiation and particulate radiation. So electromagnetic radiation is basically the transfer of energy through space in the form of radio frequency, infrared, visible light, ultraviolet, X-rays, and gamma rays. Particulate radiation, on the other hand, is about the radiation of energy by means of these fast-moving subatomic particles comprised of the electrons, the positrons, the protons, and the neutrons. In electromagnetic radiation, the electric and magnetic waves travel through space at the speed of light, consisting of oscillating electric and magnetic fields, which are at right angles to each other, and also the direction of the wave propagation. These are characterized by their amplitude, which is the intensity defined by the height of the wavelength, which refers to the distance between successive crests of waves, frequency, which is the number of wave oscillations per unit of time and expressed in cycles per second or in hertz, and speed, which is the equivalent of the speed of light. For X-rays, wavelength is expressed in nanometer while frequency is expressed in hertz. So electromagnetic spectrum as a function of wavelength and frequency is a way of ordering or grouping these electromagnetic radiations. All of the members of the electromagnetic spectrum have the same velocity as the speed of light, and they vary only in their energy, wavelength, and frequency. These are actually arranged from lowest energy to highest, starting with the usual radio waves coming from your radio, the TV, the MRI, and on the other side of the spectrum are the gamma rays used also in diagnostic imaging, particularly in nuclear medicine. So this is just a diagram of the electromagnetic radiation spectrum and its application in our daily lives. Take note that the energy form used in diagnostic radiology comes from the higher form coming from X-rays and gamma rays, which can be harmful or beneficial. So electromagnetic spectrum as a function of photon energy relates to the existence of this energy as discrete quantities of energy called photons, which may behave as waves or particles but have no mass. Electromagnetic spectra range from radio waves to X-rays and gamma rays. When interactions with matter are considered, electromagnetic radiation is generally treated as a series of individual particles known as photons. The energy of each photon is given by this formula, wherein the photon energy is directly proportional to frequency and inversely proportional to the wavelength. In diagnostic radiology, the photon energy is usually expressed in units of keV, wherein 1 keV is equivalent to 1000 eV. In diagnostic radiology, the only particulate radiation that needs to be considered is the electron with its rest mass equivalent, as you can see in this slide, and its rest energy equivalent to 511 keV. On the lower end of the electromagnetic radiation spectrum are the non-ionizing radiation, such as the visible light, infrared, and radio frequency. Okay, so electromagnetic radiation with sufficient energy to remove electrons is called ionizing radiation, which we are particularly interested in the field of diagnostic, since it includes X-rays and gamma rays. Ionizing radiation can directly ionize matter by these fast charged particles through electrostatic interactions with orbital electrons along the particle track, and indirectly through the uncharged particles such as the X-ray, the gamma rays, and neutrons that transfer to fast charged particles then directly into the matter. So matter is made up of atoms which are composed of the positively charged protons and the neutrons in the central nucleus, and it is surrounded by the negatively charged electrons. Most of the mass of the atom is concentrated in the atomic nucleus, wherein the number of the neutrally charged neutrons affect the stability of the nucleus. Mu is the unit used for specifying masses of atoms, wherein 1 mu is equivalent to 1/12 of the mass of the 12 carbon atom. So then the atomic number, denoted by Z, is the number of protons in the nucleus of an atom, and it is unique for each element, as you can see in these sample elements of cobalt, cesium, and radium. The mass number, denoted by A, on the other hand, is the total number of protons and neutrons in the nucleus. The empirical relation between these data is explained by this formula. So isotopes of a given element have in the nucleus the same number of protons but different numbers of neutrons, as seen in this example of the hydrogen and the carbon. So X-rays are basically generated by two different processes known as the Bremsstrahlung radiation and the characteristic X-ray production through ionization. So characteristic radiation is produced when an incoming electron interacts with an inner shell electron and both are ejected. When one of the outer shell electrons moves to fill the inner shell vacancy, the excess energy is emitted as characteristic radiation. When charged particles pass through matter, they interact with the atomic electrons and they lose energy through the process of ionization and excitation. If the transferred energy exceeds the binding energy of the outer shell electrons, ionization occurs, resulting in the electron ejected from the atom. An iron pair consisting of the ejected electron and the ionized positively charged atom is then formed. So the energy lost from the ejected electron is converted directly to a photon. The average energy required to produce an iron pair in air or soft tissue for electrons is equal to 33.97 eV. So whenever a vacancy is created in an inner electron shell, it is filled by an electron from a more distant or outer shell. This results in a vacancy in the second outer shell, which is then filled up by an electron, if available, from an even more distant outer shell, and the whole process repeats, producing a cascade of transitions. So the energy released in each transition is carried away by the emission of electromagnetic radiation, which depend on the atomic number of the material and the electronic shells involved. In terms of X-rays, they are known as characteristic or the fluorescent X-rays. Sometimes, after the ejection of another outer shell electron, the excess energy may also be emitted, known as Auger electron, rather than the characteristic radiation. In Bremsstrahlung radiation, X-rays are produced when incident electrons interact with nuclear electric fields, which slow them down or break them, and then they change their direction. The energy is then transferred to a photon, which is also emitted and can take any value from 0 up to the energy of the initial electron, thereby producing a continuous spectrum. So the majority of X-rays produced in X-ray tubes are via the Bremsstrahlung process. So we are done with the physics part of it. Take a breather as we move on with its application. So we now go with the diagnostic imaging methods illustrated by the subsequent sample images. This is an example of a conventional radiography or X-ray image of the chest. The second image is taken in a contrast X-ray procedure of the abdomen, emphasizing the contrast opacification of the bowel segments, particularly the colon. The third image is a sample of the brain MRI, while these last batch of images are representative images of A PET scan, wherein the purple spots that light up may represent pathologic processes taken up by the radiologic drug tracer. So, conventional radiographic examination of the body dates back to the genesis of diagnostic radiology in 1895 when Mr. Wilhelm Röntgen produced the first X-ray film image of his wife's hand. Conventional radiography remains fundamental to the practice of diagnostic imaging. So X-rays are a form of radiant energy similar in many ways to visible light. They differ from visible light in that they have a very short wavelength and they are able to penetrate many substances that are opaque to light. Film radiography utilizes screen film system within a film cassette wherein the X-rays pass through the human body by attenuating its interaction with body tissues, producing image pattern on film. Computed radiography is a filmless system that eliminates chemical processing involved in film radiography. Instead, it provides digital radiographic images which can be directly transferred to a computerized picture archiving and communication system or PACS. So the PACS stores and transmits digital images via computer networks to give the physicians and healthcare providers in many locations simultaneous instant access to the diagnostic images. So this is an example of the X-ray machine wherein the X-ray tube contain a negatively charged cathode containing the filament that serves as an electron source. So the anode is positively charged and it includes the target when X-rays are produced. The anode and cathode are contained in an evacuated envelope to prevent the electrons from colliding with gas molecules. The envelope is contained in a tube housing that protects and insulates the tube and provides shielding to prevent leakage radiation. The primary X-rays, they exit through a window in the tube housing. So as the X-rays pass through the human body, they are attenuated by interaction with body tissues. They produce an image pattern on the film that is recognizable as the human anatomy. The supine AP radiograph of the abdomen reveals the patient's anatomy because anatomic structures differ in their capacity to attenuate X-rays that pass through the patient. So the stomach, denoted by S, and the duodenum, denoted by D, are visualized because air in the lumen is of different radiographic density than the soft tissues that surround the GI tract. Okay, so most radiographic views are named on the basis of the way that the X-ray beam passes through the patient. So a posterior-anterior chest radiograph is one in which the X-ray beam passes through the back of the patient and exits through the front of the patient to expose an X-ray detector positioned against the patient's chest. An anteroposterior chest radiograph is exposed by an X-ray beam passing through the patient from front to back. And a craniocaudal mammogram is produced by passing a beam through the breast in a vertical cranial to caudal standing or sitting. So views are additionally named by identifying the position of the patient, such as in erect, supine, or prone views. So this is an example of a chest radiograph taken in posterior, anterior, and lateral views. So conventional radiographs demonstrate 5 basic radiographic densities: air, fat, soft tissue, bone, and metal or X-ray contrast agents. So air attenuates very little of the X-ray beam, allowing nearly the full force of the beam to blacken the image. Bone, metal, and radiographic contrast agents attenuate a large portion of the X-ray beam, allowing very little radiation to blacken the image. Thus, bone, metallic objects, and structures opacified by X-ray contrast agents, they appear white on radiographs. Fat and soft tissues attenuate intermediate amounts of the X-ray, resulting in proportional degrees of image blackening or shades of gray. So We now go with the cross-sectional imaging techniques. So CT, MR, and ultrasound are techniques that produce cross-sectional images of the body. All three interrogate a three-dimensional volume or slice of patient tissue to produce a two-dimensional image. So the resulting image is made up of a matrix of picture elements, which is called pixels, each of which represents a volume element called voxel of patient tissue. So the tissue composition of the voxel is averaged or volume average for display as a pixel. CT and MR assign a numerical value to each picture element in the matrix, wherein to produce an anatomic image, shades of gray are assigned to ranges of pixel values. So this is a diagram of a CT scanner. So the patient is placed on an examination couch within the core of the CT unit, an X-ray tube that rotates 360 degrees around the patient, producing pulses of radiation that pass through the patient. So transmitted X-rays are detected by a circumferential bank of radiation detectors. X-ray transmission data are then sent to a computer which uses an assigned algorithm to calculate the matrix of CT numbers used to produce the anatomic cross-sectional image. This is an example of an actual CT scan machine. As previously mentioned, CT numbers are assigned to each pixel in the image by a computer algorithm that uses as data these measurements of transmitted X-rays represented by Hounsfield unit, which is actually a scale named for Sir Godfrey Hounsfield, who is the inventor of CT. Water is assigned a value of 0 Hounsfield, but with the scale extending from positive 1024 Hounsfield for air to up to 3000 to 4000 Hounsfield for very dense bone. So a multi-detector helical CT is a major technical advance in CT imaging, utilizing the principles of the helical scanner but incorporating multiple rows of detector rings, which allows acquisition of multiple slices per tube rotation, increasing the area of the patient that can be covered in a given time by the X-ray beam. The advantage is speed, which is 5 to 8 times faster than the single slice helical CT. It allows image reconstruction in any anatomic plane without loss of resolution. Broad area coverage allows for high detail CT angiography and virtual CT colonoscopy and bronchoscopy. So this is an example image of a CT angiography illustrating the three-dimensional shaded surface display of the aorta and its branches created from a series of axial plane multi-detector CT images obtained from contrast administration. So MR is a technique that produces tomographic images by means of magnetic fields and radio waves, while CT only evaluates its single tissue parameter, X-ray attenuation. MR analyzes multiple tissue characteristics, including the hydrogen or the proton density, T1 and T2 relaxation times of tissue, and blood flow within the tissue. The soft tissue contrast provided by MR is substantially better than for any other imaging modality. So most tissues can be differentiated by significant differences in their characteristic T1 and T2 relaxation times. T1 is a measure of a proton's ability to exchange energy with its surrounding chemical matrix. It is a measure of how quickly a tissue can become magnetized. T2 conveys how quickly a given tissue loses its magnetization. So this is an example image of a brain MRI in T2 sequence emphasizing differences in the T2 relaxation times of tissues while minimizing differences in T1 times. So tissues with long T2 times are relatively bright as seen in the ventricles containing the CSF, while those with short T2 times are relatively dark. So the advantages of MR include its outstanding soft tissue contrast resolution, the ability to provide images in any anatomic plane, and absence of ionizing radiation. MR, however, is limited in its ability to demonstrate dense bone detail or calcifications, as long imaging times for many pulse sequences, limited spatial resolution compared with CT, limited availability in some geographic areas, and of course, it is expensive. Because of the physically confining space for the patient within the magnet, a number of patients experience symptoms of claustrophobia and they require sedation or simply are unable to tolerate MR scanning. So, ultrasound imaging is performed by the using the pulsed echo technique, wherein the ultrasound transducer converts electrical energy to a brief pulse of high frequency sound energy that is transmitted into patient tissues. So the ultrasound transducer then becomes a receiver detecting echoes of sound energy reflected from tissue. So the depth of any particular echo is determined by measuring the round trip time of light or the transmitted pulse and the returning echo, and by calculating the depth of the reflecting tissue interface by assuming an average speed of sound in tissues of 1,540 meters per second. Okay, so most medical imaging is performed using ultrasound transducers that produce sound pulses in the frequency range of 1 to 17 megahertz. Higher frequencies, those of ranging from 5 to 10 megahertz, yield the greatest spatial resolution, but they are restricted by limited penetration. It is routinely used for endoluminal applications, examination of superficial structures such as thyroid, breast, and testes, and examination of infants, children, and small adults. Lower frequencies, ranging from 1 to 3.5 megahertz, on the other hand, enable better penetration of tissues, but of course at the cost of poorer resolution. So lower frequency transducers are used for most abdominal, pelvic, and obstetric applications. So Doppler ultrasound is an important adjunct to real-time grayscale imaging. The Doppler effect, it is a shift in the frequency of returning echoes compared with the transmitted pulse caused by reflection of the sound wave from a moving object. So in medical imaging, the moving objects of interest are the RBC flowing blood. If blood flow is relatively away from the face of the transducer, the echo frequency is shifted lower. If blood flow is relatively toward the face of the transducer, the echo frequency is shifted higher. So the amount of frequency shift is proportional to the relative velocity of the RBC. Nuclear medicine studies provide high functional resolution and provide physiologic and functional information not otherwise available in your radiographic, ultrasonographic, and MR studies. So it involves the use of gamma rays, which, if you can recall from the earlier slides, are on the higher energy form of the electromagnetic radiation spectrum. So the most commonly used radionuclide is technetium-99m, which is injected as a technetium salt or combined with other complex molecules that permits assessment of specific parts of the body. After injection, and depending on how much the radiopharmaceutical is absorbed, distributed and metabolized, and excreted by the body, images are obtained using a gamma camera. So this is the actual procedure involving the nuclear medicine facility. The small monitor on your right, it represents the images of a particular target body anatomy taking up the radionuclide. So in this decade of advancing functional imaging, many new important techniques have become commonplace in the clinical environment. Positron emission tomography, or PET, is one of these advanced imaging modality under the nuclear medicine, utilizing positron emitted from the decay of proton-rich radionuclides. So this modality has improved the sensitivity and specificity for neural, cardiac, and oncological imaging, and even plays a greater role in tumor staging and evaluation of tumor responses to therapy. So the most commonly used PET radionuclide is fluorodeoxyglucose, labeled with fluorine 18, which is the positron emitter, in which tissues who are actively metabolizing glucose, such as in tumor or infection, take up the FDG F18. The localized high concentration of the molecule detected as a hotspot is suspicious for a pathology. I think this is the last slide for this lecture. For listening, and stay safe always.